I think by now people are convinced as to why scientists are studying comets to get at the early properties of the solar system, but it's actually a much more difficult process to get down to the interesting things about bringing ingredients to Earth that were essential to life and prebiotic chemistry. But since I'm talking about epoxy, I thought I'd start with some information about missions prior to the epoxy mission, and in fact give you an appreciation for how recent a lot of the cometary science has been. We didn't actually have proof that a comet was a very small icy body with organics in it until the Giotto mission in 1986, which actually imaged the solid nucleus and discovered that most of the volatiles were water and found organic compounds on the surface. What we've seen with missions since then is that the comets are very diverse physically. From the Deep Impact mission in particular, we learned that the surface materials are very insulating against solar radiation, which was good news. That means very primitive, unprocessed materials may lie directly beneath the surface layers. And as we've seen from the Stardust mission, apparently there was a lot of mixing in the nebula because comets aren't just cold, icy remnants of the early solar system. They contain a mixture of high temperature and low temperature materials. Well, the Deep Impact mission in 2005 was highly successful, and immediately after this mission, remember the mission was an impact where two spacecraft separated, and one impacted Comet Tempel 1 with the intent of digging beneath the older process layers. Because of the scientific success and the very large public success, this is an image of 10,000 people on Waikiki Beach watching the event unfold, NASA allowed the mission to have an extended mission, and this was directed to go to Comet 103P Hartley 2, not because it was a compelling scientific target on its own, but like many missions, because we could get there. It was interesting, though, because it was going to be very different from previously investigated comets, namely that it's small and was known to be very active. So we were going to compare the surface geology and chemistry in an encounter in last November. All right, part of this mission involved a very large ground-based campaign because missions are fast flybys. This one was a 12-kilometer-per-second flyby at almost 700 kilometers from the nucleus. So much of the information about the target needs to be obtained over timescales and at wavelengths and with instruments that are simply not possible on board the spacecraft. So this campaign involved most of the world's major observatories as well as a large suite of amateurs. This both informs the mission to help better prepare for the mission and provides a timeline and also other information for interpreting the data. Now, one of the early interesting results from this campaign was we started to look at the comet as soon as possible after it had passed aphelion, its most distant point in its orbit where it was coldest and should be effectively an inert object that looks very much like an asteroid. Much to our surprise, about 9 months after aphelion, the comet was imaged. It was recovered very faint with a 8-meter telescope, and it seemed to have a tail. It seemed to be active. Now, the way comets become active is sunlight warms the ices, they sublimate and drag out the gas, which is what we measure at these large distances. This was confirmed with the Spitzer infrared telescope in orbit that showed that not only was there some dust there, it must be very large grains. However, about 9 months later, with another large telescope, the dust was gone. This image, which is a composite of many images, the streaks are stars added together, shows no evidence of any dust at this point, so it ceased its activity. Now, one of the things you could do when it was so far from the sun, you couldn't do much because it's very faint. We could look at the modulation of its brightness to look at the rotational light curve. This is important not only to help plan for the mission, but to understand how the heat gets distributed on the surface and interpret the data we see at an encounter. And what we found was that it rotated with a period of about 16.4 hours. But this unusual light curve shape with this bump was suggestive of something that was really flat or perhaps a bilobate structure. Now, most of the ground-based observers couldn't start to get rotation until 2010, just a few months before the encounter because the comet was so faint. After it came out of solar conjunction, they started to observe it, but at this point it was warm enough that it had developed its large cloud of gas and dust, and so now observers are using these jets to monitor the rotation period. What we found was, surprisingly, that the period was changing fairly rapidly. It was slowing down during the fall, and then the Arecibo radar did confirm that it had a very unusual shape. The encounter was very interesting. Like all the previous encounters, this was a very different sort of object. We saw a nucleus with strong jets coming off in the sunward direction, even some in the nighttime side. And when you looked with the imaging spectrometer to develop images at different wavelengths sensitive to different molecules and reflection from dust, we found to our surprise that the dust was driven off entirely by the carbon dioxide jets, which was also driving off ice, and that water, which we had thought to be the main driver of cometary activity in the past, wasn't responsible for removing the bulk of the dust from the surface of the nucleus. Looking up close with the high-resolution imager, once the images were deconvolved, we saw a veritable snowstorm of particles near the nucleus, very close to the nucleus, and depending on what albedo or brightness you assign to these particles, they were either centimeter scale or up to meters in size, so very large compared to the usual dust we see coming off of cometary surfaces. This led to an image that maybe the water is coming off diffusely over the entire surface, but this comet in particular has jets of carbon dioxide that are arising from deeper subsurface layers, which are driving out gases at higher velocities. Now, I don't have time to go through all the wealth of ground-based observations, but many teams stretching from ultraviolet to radio wavelengths were looking at the gas species, and they found that this comet was typical of many of the comets that Dominique had reported on earlier in this session, with the exception that this one seemed to be extraordinarily low in carbon monoxide. Likewise, the teams of observers looking at the dust component found that the dust in this comet were typical of many other comets, except that there was evidence for very large dust particles. Arecibo actually imaged or got radar signals from the dust cloud. Now, one thing I wanted to comment on was one of the unique aspects of the ground-based observations over time is that we could watch this comet develop from inactivity to activity by combining all of the ground-based data of the scattered light from the dust and then compare it to a simple sublimation model of the types of ices that might be present in the interior. Now, normally this sort of model is largely unconstrained, but for this comet, because of the space mission and the wealth of resources that looked at the surface, we could actually have a lot of constraints for our model that we would then see if our model matched what was observed in situ and from the ground. So this shows a plot of brightness where, on this scale, we have removed the changing comet-sun and comet-Earth geometry. So a bare nucleus that has no dust coming off the surface should look like a horizontal line. The data points here and all the colors are the various observers, and then the solid colored lines represent various models. So starting with the assumption that this comet was activated by water ice sublimation, this is the blue curve here, and it fits pretty well until we get fairly close to the sun a couple months before perihelion, and then it fails. What we had to do was add a lot of carbon dioxide, as shown with this orange curve, to make the curves fit. Now, normally carbon dioxide is an ice that sublimates at a much lower temperature than water, so you would expect if there's a lot of carbon dioxide, it would be active all the time. But in fact, what we had to do was bury the carbon dioxide deep within the comet so that it took a while for the heat to get from the surface down to the carbon dioxide. This is just a blow-up of the model showing it fits nicely. The one thing that didn't fit with this multi-component model at first was the measured water output as seen from various ground-based facilities and orbital facilities. In order to make the water production match, we had to assume that these big particles floating around the comet, which were seen by the spacecraft, were in fact icy and also outgassing. One thing that one can do, and postdoc in Hawaii, Gal Sarid, has just started to do this, is to look at, is it reasonable to expect that CO2 is going to be here? It's a very volatile ice, and if this comet, which is very small, it's a little over ½ a kilometer in radius, has been in the inner solar system for very long, shouldn't this ice be gone? So he's taken a very first cut, sort of a worst case scenario, This will be dependent on where the rotation pole is. If it's tipped way over, you can preserve ice more easily. It will depend on how long this comet has been in this orbit. We don't know in particular, but we do know in 1972 this comet made a very close pass to Jupiter, and prior to that it was further out. But what he shows is that the CO2 should actually disappear relatively quickly, at least in the worst case scenario, but that it will migrate down to a depth of a few meters where we might have solid ice still existing. And it may in fact be quite patchy, and this is consistent with maybe seeing outgassing from jets as the heat wave penetrates down to depths within the comet. So what are the implications? This is really the first comet we've had some very nice evidence that the dust is driven off by CO2 instead of water. One thing that's interesting is if you look at some of the statistical data sets that have been accumulated, Mike Ahern in 1995 published a very nice paper on water production and other species coming from comets. What he didn't have at the time was the sizes of those comets. And when you combine this with some more recent statistical surveys of nucleus sizes, what we find is that most comets don't seem to be very active. A few % of their surface is outgassing water. But there's a handful of comets, including 103P Hartley, that seem to be more than 100% active with water. This just means maybe, like Hartley, they have huge clouds of icy particles around them that are also sublimating, and maybe this suggests that the icy particles are in fact driven off by something more volatile, such as CO2. So the question is this an evolutionary effect? Do we have different sets of comets that we see behave very differently because some are just coming in for the first time? Or is this something more interesting from the primordial perspective? Do we have very different chemistries in comets that we're just starting to see because we're just starting to get the technology and the long-term baselines to look at the comets? And just getting back to this final slide, the one I started with, remember again, we really only proved that comets had a solid body in 1986.